How's it going out there? So previously on monadic design patterns for the web, we looked at monads as not so fuzzy warm things. We saw there were three key ingredients to shapely monads: shape, wrap, and roll. We looked at data structures as colored braces, and we saw that the colors were the shape, the wrap was putting things in between the braces, and roll was rolling up those nested braces. Last time, we looked at two kinds of collections: extensional collections, which we can explicitly give each element of the collection, and intensional collections, where we have to specify the elements of the collection programmatically. And we noticed that there were several different syntaxes for intensional collections, and I left one off, and I hope that maybe someone out there in the audience who saw the previous one noticed what it was and said, "Hey dude, why didn't you mention, and what is it? Wait for it, what is it?" IEnumerable. That's the other syntax that goes here. So essentially, LINQ is yet another way of doing exactly this. And then we began to suggest that maybe there were three kinds of monads. Monads where stuff goes in and doesn't come out, monads where stuff goes in and sometimes can come out, and monads where you have this linear balance. Everything that goes in is matched by something that comes out. And to begin to illustrate these ideas, we started to look at the connections to control. We skipped the connection to logic, and we intimated that there would be a co-connection, which is how to start composing monads, and in particular, how to start composing monads with an interface that allows you to get stuff out, which we might think of as co-monads. Okay, so again, we talked about monads as not so fuzzy warm things, and in the middle of that video, we made an oblique reference to hats, okay? So you're wondering, why was this crazy, weird, oblique reference to people not wearing enough hats? And that's because we're in the process of making a connection between monad and control that is going to allow us to pull the rabbit out of the hat. Okay, so what we did was we sort of imagined a key value database up in the sky. We sort of thought about computations that were in various stages that were accessing the key values, and we talked a little bit about how that structure can be utilized to both give us transactional semantics and data structure semantics if we're careful about the way we arrange the flow. So what we're going to show is how to get the rabbit out of the hat, which means how a regular Joe can use shape, wrap, and roll to get into the flow. Whoops, must have been the wrong hat. So regular Joe, we don't want to confuse with some other moose, because regular Joe is always thinking about how to get manage system requirements in terms of the resources available. And regular Joe is very orderly, so he writes down rules, and we're just going to show a few rules about how to get meet system requirements in terms of resources. So what are those rules? I'm going to go slow. So far I've been going really fast. I'm going to go really slow on these rules because in practicing this with other folks, I noticed that it takes a while for this stuff to sink in. So the basic idea is if we're resourced with some collection of resources R, and that allows us to meet a demand for A, then with no demands on the system whatsoever, we can, with resources R, we have the right to print an IOU for A. Okay, so let's think about that very carefully. Essentially, syntactically, what's going on, if we just forget semantics, syntactically, all we're doing is we're moving the A across this funny symbol here, which we sometimes call a turnstile. And that, when we do that, what it does is it turns the A into an IOU for an A. And the thought here is that, look, if we know that from R we can meet a demand for A, then we are confident that if we wrote down a promissory note for an A, that we could fulfill the promissory note if someone came to redeem it. Okay, so this, and what I'd like you to do is keep in mind money, because I'm going to make some points about money that are directly related here, both in terms of transactional, in the real sense of transaction, and also in the sense of type, because those comments are actually cut to the heart of why trading is so complex. So again, if this collection of resources R, and remember R might be a whole collection of resources, if R allows us to meet the demand for A, then we can pull the A over here and we can be confident that we can print an IOU that we can honor. Now the dual to that idea, this is what regular Joe has in his head, is under the situation where I have no demands on the system and I've got resources R together with A, then I can move the A on the other side of the turnstile, and I know that if I give the IOU, it's something I can redeem. Okay, or something that the system can redeem. Okay, so the astute audience out there is going to be able to say, ah, look at that. Anytime the A swaps positions across the turnstile, IOU decorates it. Okay, so if we go from right to left, we accumulate an IOU. But on this side, it means we have the right to print. If we go from left to right, we accumulate an IOU. In this case, it means that we can redeem such a demand. Now, the other point here is that these A's, this is really a symbol. It's a meta object. Okay, so another way of thinking about this is that the IOUs nest. What could be in the position of an A is an IOU of an A. So if this were an IOU of an A, then when I moved the A across, I'd get an IOU of an IOU of an A. Now, again, think about money back when it was backed by the gold standard. So my little green promissory note allowed me to walk up to Fort Knox and say, please give me my chunk of gold bullion. Okay? Now, but that's where it stopped. Now on Wall Street, that's not where it stops, because you can get a promise, you can trade for promises to get an IOU, which you could then trade for gold bullion. And in fact, you can go ad infinitum. You can trade for an IOU, for an IOU, for an IOU, for an IOU, for something that you can trade in, for pork bellies or gold bullion or whatever it is. So this compositional idea is actually, compositional promissory notes, is actually not unrealistic. I mean, this kind of thing actually does exist in trading, but more interestingly, it shows something about money, which is that IOU we could think of as like a type constructor, right? Right? It takes something of type A and produces something of type IOUA. Okay, that's kind of neat. Okay, money doesn't have a type. Why? Well, because there's nothing you can say for sure. U.S. currency is not backed by anything anymore. So there's nothing that it stands for in reality, right? So that's quite interesting. Money is a typeless quantity. Another way of thinking about that is money is like void star. You know it's a pointer for something, but there's no guarantee, no safety about what it's a pointer for, right? And therein lies all kinds of ambiguity. But we'll leave those questions and ideas to one side for a minute, because I'd like to introduce a final notion. So the final notion is, so notice that we have this no demands on the system. And when I was practicing this with someone, they were asking, well, you know, why do we have this situation where we have no demands on the system? And they noticed that we can move the A over in this case because there's no other outstanding stuff related to the system. There's no other demands or requirements. And so what we'd like to do is sort of figure out what it would mean to move an A across if there are outstanding demands on the system, say B. And here, the rule is very simple. What Joe writes down in his notebook to kind of keep things straight in his mind is that if I have resources R together with the resource A, and that allows me to meet a demand for B, then with resources R, if I had an A, then I could meet a demand for B. Or another way of saying it is, this kind of thing, once we've guaranteed that this situation obtains, then we have this, the ability to create a box in which if you put in an A, you'll get out a B, given resources R. Is that making sense? Mm-hmm. Charles is over there hanging out in the corners, making sure that I don't feel too lonely. And,
exactly.
You know, because I can't see you guys out there. All right. So essentially, we can relate this back to our flow of control picture, our little key value database, because regular Joe knows where to get an A. That's essentially how to interpret this idea of resourcing, right? And we'll show that, for now, we'll just say that regular Joe knows a place where he can get an A or the A isn't present. Then we'll talk a little bit more about how we could capture Joe's state to ensure some other kind of capability. So, now the next slide I'm going to go through very, very slowly. Okay. So this is the connection. Now we're beginning to really see the connection to logic, I hope. Hopefully this makes it clear. I showed this to a guitarist. So I figure if the guitarist who's really, you know, he's a musician, he's a very bright guy, but he doesn't program, and he's certainly not a logician. If he can get it, then there's a ghost of a chance that I've been able to communicate it to a wider audience. So the first thing we start with is something that we hope to be self-evident. If Joe knows where he can get an A, then he can meet the demand for an A. Right? So if Joe knows where he can get an A, then he can meet the demand for an A. And we take that as axiomatic. That's the bedrock. You know, essentially this is, you know, a wire. You know, if you gave me an A, I can meet the demand for an A. Okay? Now the next one is really an application of one of Joe's rules. So we're going to take this A and move it across to this side. So we take the A away from here, leaving no demands on the system, and then we move it over here, creating an IOU for an A. Well, look at that. What is an IOU? It's nothing more than negation. Okay? So all we've done is say, you know, with an A, I can print a reliable backed IOU. That's what this statement says. Okay? So now, the next statement is very interesting because it says, well, once I've created this IOU, so before I do that, I just want to show the rule, okay? So the rule that we used in that first step was this one. In this case, R was the A. And why did we do that? Because we didn't have to establish an R gives you an A. Because we can feel intuitively that an A will give you an A. So once we have an A gives you an A, then we apply this rule with A standing in for R, and we move this A across according to this rule, leaving nothing here and an IOU for an A there. So that was from here to here. Now from here to here, the rule we're going to write down, or to employ, is we're going to move the A, the IOU for an A over to this side. So we'll get, and that's why I was careful to point out the compositionality of this rule. So the compositionality, in this case, we have some, ambient set of resources, which in this case is the A, and then we have an IOU for the A standing in this place. We move the A over, which is the A, which is in our instance an IOU for an A over, and we get an IOU for an IOU for an A. So that's what we did. So we take this guy. So we are free there's certain things called structural rules, which I haven't really spent a lot of time with here because it's not so important. But the commas are commutative. I'm freely allowed to flip these around. So if I just flip these around, I have an A here, which can be the R of this rule, right? And then I have an IOU for an A in this position, which would be this A. And then I move that thing across. So what do I have to do when I move it across? Well, when I move it across, I have to decorate it with another IOU. In other words, I have to go from IOU for A to IOU for A. So at this point, what we've said is, with an A, I can redeem an IOU for an IOU for an A. That's pretty interesting. Unexpected. Perhaps. Now, finally, let's just get rid of this dependence on this resource. We're just going to move it to this side, but we already have a system requirement over here. So we have to employ this rule. Okay? So we've got the R in this case is empty. We've just got an A, and we're going to move it over. That says that we make a box that when it's given an A produces a B. I don't have to be too coy here. That's a function. This is a function type, right? And then in this case, R is empty. So what does that look like? Well, that looks just like this. We move the A over. It goes on the left-hand side of the implication. And we get A implies not A. Now guess what? That's exactly 1/2 of a very famous point of view. And in fact, it's so famous and so old, it's called classical. And that classical point of view says that either we have an A or we have not A. I'm sorry, not A. Either A or not A. That must obtain. Well, it turns out that you cannot use these rules, and I will not prove it here. I invite you to go and investigate and calculate for yourself. You can't use these 3 rules to go the other direction. You'll always be one off with respect to the IOUs. So in other words, what do I mean by other direction? So we've written down A allows us to conclude IOU for A. And we'd like to be able to say something classically. The classical logician would like to say this. So this one we checked off. We can make that happen. This one we cannot check off with those rules, which says that those rules mean that we're living inside what's called intuitionistic logic, which is the logic that is most readily associated with functional programming. So whether we're talking about, Scala or Clojure or F# or C#, lambda expressions, that's the logic that is most closely aligned with the computational model. However, and this is where things get really interesting, some cool people noticed that if we could remember where regular Joe was in his computation when he asked for an A, then we could get back that classical representation. Now that's the trick with continuations. Okay, so how does this work? Suppose that Joe walks up to our little key value database and says, is there an A? And if there isn't, the key value database remembers where Joe is in his computation. Okay? Then, if someone says to Joe, so I say to Joe, or someone in the audience says to Joe, hey, A, can you meet the demand for an A? So Joe is now absolutely free to say no. Okay? Because if an A comes in and we can jump back in time to the point just after the demand for the A, but right before Joe answered, okay, then he can then produce the A and say, A. Okay? So let's see what that means logically. So a client, one of Joe's clients says A, and Joe asks the key value database A, and the key value database quickly takes a look, notices there's no A, takes a snapshot of Joe's state. That's the essence of taking a continuation, right? So you could take stack frames in the .NET VM or the Java VM, or you could do something more clever. It's a lot easier if we do something slightly different than that to do the calculations, because dealing with the stack frames would rapidly expand in terms of what we had to write down. But the main point is somehow we capture Joe's present state. So now Joe is absolutely copacetic. With all confidence, he can turn to the client and say, no A, not A. Because if no A ever shows up, well, it's true, not A. And that obtained for the rest of the lifetime of Joe and all of Joe's clients, right? For all of the engagements with Joe and the outside world, no A showed up. So it was absolutely true, not A. On the other hand, if an A does show up while Joe continues to compute, the key value database which remembered Joe's state pops that one back in, erasing the previous, the computation that we went down, sort of jumping out of the primrose path. You could call it backtracking if you want. And then Joe now has an A, but Joe is back in his original state. So then Joe, with all confidence, says A, because Joe has an A. So no matter which branch Joe takes, Joe is absolutely safe. Not A or A. And that's the classical interpretation of what's called the law of excluded middle. And that's that's the continuation interpretation of the classical law of excluded middle. And that's how we get the other side of this implication. Now, if you think about it, this is not just some abstract nonsense, because when we talk about transactions, if A is, if the client of Joe is, if Joe is really a bank, and the client of Joe is asking for money out of some bank account, then Joe goes to the account and says, "Hey, let's make this more concrete. We'll webify it. There's an eBay transaction underway, and an item is on sale. The auction has closed. The item is sold. The buyer of the item now has to remit funds. Okay, so the seller of the item goes to the buyer's financial institution, which just happens to be Joe in this case. We're trying to keep banking simple now, then Joe looks into the buyer's bank account. Now, if it appears that there's no funds, right, there's a problem, right? So then you would have to put in all the punitive damages against the buyer, etc. But if the buyer can go back to the bank and say, it was your fault, you misordered this deposit with this debit, then the nice thing to do, the reasonable negotiation here, is to go back in time to that point, remit the funds and let the transaction go through. So this really is right at the heart of a transactional behavior. Does that make sense?
Yeah.
Awesome. Okay. So when we actually get to the bridge where we wrap up, we use shape, wrap, and roll to talk about the bridge between flow and structure. What we'll really do is use a form of continuation that is not unbounded. We're actually going to have markers which say how much of the stack we can roll back. And that's called delimited continuations. And what we'll see is that the monadic presentation of delimited continuations allows us to factor the translation or the interpretation of the continuation-based behavior in such a way that we can be as ignorant as possible of the underlying implementation, whether it's continuation passing style or the use of stack frames or some other mechanism. For example, something up in the cloud in terms of key value databases. So all of the gritty details of the flow of control will be hidden underneath the shape, wrap, and roll. And that's a part of what makes this incredibly powerful. So if we think about an end-to-end web application, what we're starting to see, let me see if I have this. What we're starting to see is that when we talk about the storage model, which must be the place where we host our transactional semantics, that can also be represented and factored through a monadic presentation, which simplifies the use of our code. And if we go all the way back to the very outset of this, one of the things that I'm talking about when I talk about applications at scale is scaling the complexity of the application, which makes it more maintainable and more manageable. So that's part of the real power here in terms of monadic techniques. So in order to, hang on one second. There we go. In order to present this, what I need to do is I now need to present a number of pieces, and I need to build up a little bit of tools for doing that. So I want to go slow and do that step by step. So one of the things I want to do is introduce the idea of parametric grammars. So this is going to allow me to introduce data structures that are potentially programs. So eventually what I want to do is introduce a little programming language and build an evaluator for that little programming language. And then I want to talk about the semantics of some of the core operators of that language in terms of the low-level functions in my evaluator, and then I want to talk about factoring those low-level, factoring the translation through the monad. Now, in order to do that, I need to be able to present a little programming language. So I want to build up to the tools to present that programming language. Now, in fact, we've already done this. We did this in terms of shape, wrap, and roll, and the discussion of algebras. But I'm going to do it again. And the reason we're going to do it again is because we're going to take these little intermediate steps to the presentation of a language. And what we'll actually see is that every language is given in terms of three things. There's a grammar which freely generates all elements of the language. Now, in terms of what we've talked about before, the free generation of all elements of the language, if you replace the word language with collection, we're right back where we started, right? If we could freely generate all the elements, or programmatically delineate all the elements of a collection, so this is like the intentional specification of a collection. So if we can freely generate all the elements of our collection, a grammar is one way to talk about that. So this is a way to intentionally describe collections. And we'll see that in a minute, okay? Now, it may turn out, so what are the elements of the collection of a language? Well, they're programs, for example. Now we know that some programs, even though they're syntactically different, need to be identified. Okay? What's a really good example of that? Well, a really good example of that is one in which we have, for example, suppose I have def foo, and it takes an argument x of type t, returning type r, blah, blah, blah. And there's some expressions in x in here. Now, if I were very careful and I got rid of the x and I said, you know what, I don't like x as a name, y is a much better name. And then I went through and carefully renamed all of the places where I used x to be y, making sure that y wasn't already used as a variable in here. Like if I had outside of the scope of this introduced a y, say up here I'd said val y equals blah blah blah, and then utilize the y here, that wouldn't be the best. That wouldn't be the best. But as long as I'm careful to pick a new variable name that doesn't clash with something already there, and then I'm systematically replace the x for the y, then the foo in x and foo in y need to be the same. We need to treat them as if they were the same. So we can factor. Now, by the way, what's that like? That's exactly like the situation where we noticed that, a set union with a set is the same as a set union with the set in the opposite order, and that a set union with itself is the same as the set. Okay? So this is another instance, and so we've already presented this material. It's already there, but what we're saying is that it actually works for the specification of languages. Now, the reason that's important is because if we believe the emerging wisdom that DSL, domain-specific language-based design, has some truck, has some currency, well, then we ought to have the tools to write down languages. What are those tools? Wait, can you, I give you three guesses and the first two don't count. Monads. Okay, so the generator is actually the monad. The grammar is the monad, and it freely generates all the elements of the collection. The relations, which we now these days call structural equivalence, so grammar, structural equivalence, these are the things that whack down the set to just what we want to consider as distinct. Okay? And there's a final piece, which is the operational semantics. And this says how utterances, actually equivalence classes of utterances produced by the grammar, reduce to some other utterance. Now, we'll see this in action when we present the lambda calculus. Okay. So I'm going to present a tiny little language that's on the way to the lambda calculus. We're gonna leave it there for today. So let's go over what we've learned. So we've begun to go down the rabbit hole and look at how shape, wrap, and roll are going to get us a bridge from structure to control. Right? We're trying to put Joe, regular Joe, into the flow. So what we did in order to explain that was to hook into the connection between continuations and logic, right? So we went through exactly the rules that were necessary to produce the relationship between A and IOUs for A, and then we showed that the continuation technology was necessary to give us a classical style evaluation and how that was related to transactional semantics. And now, but that was all, at skating along the surface. Now to go deep down into this, we're going to have to introduce a programming language, introduce its evaluation, and show how the monads allow us to factor all of that. And then finally, in the rest of the series, we'll talk about how to nest or situate all of that inside a web container, which allows us to write the programs in the programming language and execute them. So stay tuned. Hope to see you next time.
Great.
Sweet.